Okay, so in this lecture, I'm going to introduce chapter 3, and I'm going to walk you through the basic story of fitting linear models, first using just an intercept, and then using a predictor, a single predictor. And the only complexity in the Bayesian approach that takes us beyond the standard frequentist linear modeling framework is the issue of prior specification and the way in which the model is evaluated using prior predictive and posterior predictive checks. So these are the only two important developments in the Bayesian framework when it comes to fitting simple linear models. I'm going to first share my screen and walk you through the slides. I believe that most of you are already familiar with the linear modeling framework. So assuming that, I think I can go pretty quickly through the basic setup and just focus on the novel aspects of Bayesian modeling in the context of linear models. So just to remind you where we are at, so we're talking about trying to obtain posterior distributions of the parameter or parameters of interest, right? So the model that we are actually fitting involves a likelihood function and prior specifications on possibly multiple parameters. So this big theta here, the capital theta, represents multiple parameters that might be present in the model. So it's a very general statement here for arbitrarily complex models. And what we get as a result of the Bayesian computation is the joint posterior distribution of all the parameters. And from that joint posterior, we can derive, like I showed you in chapter 1, I think, we derived we can derive the marginal distributions of each of the parameters, which is what we usually do our inferences on. Okay, so in the analytical cases that I discussed over the last few weeks, basically what was going on there was that we were able to come up with an analytical form for the posterior without doing any computational work. So basically, the end of the day, with the Poisson gamma conjugate case, or the normal conjugate case, or the exponential gamma conjugate case, any of those cases, or beta binomial, what happened was that we had a closed form probability mass function or density function, or probability density function, sorry, for the parameter of interest in each case, right? So all we have to do, for example, in the Poisson gamma situation, all we need to do is know the total number of data points n and the sum of those data points, right? And if we know those two things and we know the A and B parameters on the prior for the lambda parameter, then we can derive the posterior. So we don't actually need to do any computational work as such, because once we know the posterior, we can just use the DPQR family of functions to figure out our uncertainty of the posterior distribution and based on what we learned from the data, right? So the DPQR family of functions gives us everything that we need to know about the posterior distribution um, without having to do any MCMC sampling or something like that. So that is what allows us, to, in the example I showed probably in class or in the homework or something. So there was a problem where we had a prior on lambda, we had some data, Poisson distributed, and then we derived the posterior for the lambda parameter in the Poisson distribution, and we come up with the posterior distribution for the lambda parameter. And so this plot that I'm drawing here, so the red line is the prior and the black line is the posterior. So these plots are actually based on analytical results. So if I want to know, what's the 95% credible interval in this distribution, in the gamma 27 distribution, then I can look it up. I can figure it out using the DPQR family of functions, right? So there's no need to try to do any computational work to work this out. But and so the way I would do that is if for a particular distribution, like let's say this is the posterior distribution, shape 20, rate 7. That was the posterior I just showed you here, right? So in this posterior, if I want to know what the 95% credible interval is, I just use the Q gamma function and I know the range, right? This is just an analytical result that I can derive, can work out using these built-in functions. But what's going to happen in the future now is that there won't be any conjugate cases that we're working with. So what that means is we might have a particular likelihood, for example, a Poisson likelihood for representing the generative process for the data, but for the lambda parameter in the Poisson likelihood, we might choose some other arbitrary prior that need not be a gamma prior, okay? And in that case, we won't get a conjugate situation again. That means our posterior would not be of the same family as the prior anymore. And there, we're going to have to use computational tools to get this posterior distribution, right? So, or some posterior distribution that's, representing the posterior on lambda. It won't be a gamma anymore because we don't have a conjugate case anymore. And so, what we will be the problem we'll be facing is to how to describe this distribution, how to even graph it, how to plot the distribution so we can see what it looks like. So what we will have to do is we are going to have to use something analogous to the R family of functions. So for example, in the analytical Poisson gamma case that I mentioned earlier, I could have actually just generated 4,000 samples from the posterior. So there's the posterior samples that I've got from the R gamma function. And then I could go ahead and use those samples to calculate the 95% credible interval. So if we compare these numbers, the analytical credible intervals 1.74 and 4.23 with the intervals computed using Monte Carlo sampling, right? You'll see that the estimates are pretty close. They're not identical, but they are very, very close. And so if I increase the number of samples, I'll get even closer to the analytical numbers here. Okay, so in the coming lectures, whenever I talk about getting samples from a posterior distribution, what I'm talking about is the analogous step to what I've done here. I'm obtaining 4,000 samples here from a gamma distribution by just using the R family of functions. So what will change for us in the computational setting is that we won't have any analytical posterior. We will just have samples from the posterior. We don't know what the form of the distribution is necessarily that is producing the posterior. All we have is the samples, but that's okay because once I have the samples, I can just do my statistics on those samples. I can draw my inferences from the posterior, right? So the switch goes from the analytical analysis that I've been doing so far to computational generation of samples for each posterior, and then drawing inferences on the posteriors by using things like the quantile function to figure out the credible interval and things like that, right? So whenever I say that we will be obtaining samples from the posterior distributions, this is what I'm really talking about here, right? We're actually going to get samples from the Stan programming language. Once we fit the model, we will have samples from the posteriors of all the parameters, and we can examine them and do statistics on those posteriors, like the mean, median, 95% credible interval. All these things can be computed from the posterior. Okay, so coming back to our main goal, which is to derive the posterior distributions of the parameters given the data, right? We'll be using MCMC sampling to obtain these posterior samples, and now we're going to look at some practical examples on how this would work. Now, I think that because all of you already understand linear modeling, um, I will just give you a quick overview of where I'm going next, and then I'll quickly go through the important things that are new, okay, in the whole story. So coming back to my iPad here, what I want to point out is that we are starting with this simple linear modeling framework where we have some dependent measure y, and we first start by just modeling the dependent measure y with a fixed intercept, okay, an intercept, and assume some residual error here. So really what I'm talking about is something like this, right? So um, um, how should I do this? Yeah, so let's assume that the data, I'm just making some data up here, right? So the data could look like this, right? There could be some data like this. And so if I were to find the average value of those data, that would be this intercept here, beta 0, right? And what this epsilon actually tells us is the deviation. These are the residuals in this linear model, which are telling us the the distance from the estimated beta parameter, right? So the beta parameter that we are estimating here will um, be, in some sense, the best fit to the data. And by best fit, what I mean is it's using something called least squares, the least squares criterion to minimize the average square distance, between the horizontal black line and the actually observed data line. So it's kind of the center of gravity of all those data points. And so the residuals here are assumed to be, this is in the frequentist world, independent and identically distributed with mean 0 and some residual standard deviation sigma, which is representing the standard deviation, the extent to which the dots are far away from the black line, right? So that's basically the standard linear modeling framework in the frequentist setting. And the only elaboration that we'll discuss, in the next step that we will discuss in the linear model is that we'll have y as a dependent variable, there'll be an intercept, plus there will be a slope, right, with some predictor x that is going to um, be added to the linear model. And the idea here is, so a simple example would be if I'm trying to model um, weight, individuals' weights as a function of their heights, that's an example. Another example would be child IQ, child IQ as a function of mother's IQ, right? That's another example. And so in these kinds of situations, what I'm talking about is that, let's just take the child and mother IQ example. So the mother's IQ is on the x-axis, child's IQ is on the y-axis. And what we're talking about is a model that's roughly like this, right? And the data might look like this. Just making something up here. And so what this model is now saying is that, first of all, there is some residual error. There's a non-zero error here, right? And secondly, what this model would be saying is that the for the value 0 here, let's say if 0 is on the x-axis here, then the predicted IQ of the child, predicted IQ of the child is here. This would be the intercept, right? Technically, that would be the intercept, right? That's the beta sub 0. And the slope dy over dx, right? That slope would be represented as beta 1. So what the model says is that the child's IQ, that is y, is a function of some average IQ when the mother's IQ is represented as 0. which is of course nonsensical, but technically that's what it would mean. And uh, the beta 1 parameter would be telling us what the predicted increase in the child IQ would be for 1 unit increase in the mother's IQ, right? That's what the model actually does. It gives you a prediction for how the child's IQ would increase with 1 unit increase in the mother IQ, um, by how much it would increase. And this epsilon term is, of course, the residual error again, which is telling you the extent of the deviation of the actually observed data relative to the um, the fitted models, predictions. Okay, so that's the basic framework that we are going to work with. We're going to have either only an intercept, or we're going to have an intercept and a slope. And then later on, I'm going to start elaborating on more and more, adding more and more structure to this linear model to convert it to a hierarchical model. All right, so the example data set we're going to work with is a data set that was created with a single subject. That's Bruno Niesenboim, the first author of the textbook, right? What he did was he just sat down and pressed the space bar repeatedly on the computer and used a software to record his button pressing times, right? So what we have is the data frame space bar, and there's a trial ID in this data frame and the button pressing time in milliseconds in this data frame. So this is a pretty standard and simple setup that we use a lot in psycholinguistics, where we are studying self-paced reading. We also have people read sentences word by word by pressing a space bar, right? So there's actually a package. What is this package called? Right, so there's actually a package. I don't know if it exists anymore now, but yeah, so there's the package called Linger that allows you to run language processing experiments, and it can run self-paced reading studies, and it's a very standard software that's used quite widely, or used to be at least used quite widely for running these kinds of experiments. And you can see a visualization here of how the experiment runs, right? You start the sentence by just looking at a bunch of lines on the screen, and every time you press the space bar, you see one word in the sentence, and the amount of time you spend looking at each word is recorded through the computer via the space bar press. So we are just doing a toy version of that experiment here, but we're just mindlessly pressing the space bar. That's it. And so the response times are what we're going to now model. That's our dependent measure. And so we're going to try to study the properties of this distribution here. First of all, if you plot the distribution of button pressing times, you'll see that it has a distinctive right skew here. That is very common in reaction time and reading time data, because reading times and reaction times cannot go below 0, so they can only increase in one direction. So you will see this distinctive skew towards the right. And so that also should be an indication to you that these data are not best modeled with a normal likelihood, because a normal likelihood is symmetrical, right? And so we don't have a symmetrical distribution here. So eventually what we're going to do is, when we properly start modeling this kind of data, we are going to use an appropriate likelihood function. But for now, we're going to work with the normal likelihood, which is completely unrealistic, but doesn't matter for now. Okay? For starters, it's okay. So we're going to assume a normal likelihood that's producing these data. And so let's unpack this model. So first of all, notice that the likelihood function contains two parameters, mu and sigma. So there's two parameters that need prior specifications. Just like in the beta binomial, Poisson gamma, exponential gamma cases that we saw earlier, we had a parameter or parameters in the likelihood function, and our job was to figure out some prior for that likelihood, for that parameter, and then derive the posterior for that parameter. So this time we have two parameters, so we have to define some priors for these. So the way that in the entire book, the way we will talk about data is as follows. So whenever we have any data set that we are looking at, we are always going to consider the generative process that produced each row in the data frame. So what I mean by this is, let me just um, set this up. Um, so so what I want to be doing is, in these data, um, in the whole book that we'll be, when we are doing statistical modeling, we will try to describe how each row in the data frame was generated, right? And for that reason, we're going to label the rows with an index that is this subscript n here, right? So when I say t subscript n, t is the response time or button pressing time or whatever, the the subscript n represents the nth row in the data frame. So what we are assuming here is that every data point in the entire data frame is being generated from a single normal distribution with a single mean and a single standard deviation. Okay. So the linear model is what I just showed you earlier when I wrote it down on the iPad. So we've got a simple linear model here. This is my intercept. This mu is representing the intercept and is also the mu in the normal likelihood. So these two statements that you're looking at here, they're exactly the same statement, right? So a linear model is just assuming a Gaussian likelihood of, for producing the data, and that's why these two statements are equivalent. And the epsilons here are basically representing this residual standard deviation, and they assumed these residual terms, and there's going to be n of them, right? Because there are n rows. These residual terms, this residual term is going to be assumed to be independent and identically distributed. That means every single residual term, every one of those n residual terms is going to be independent of every other residual term and is going to be identically distributed, right? So there's one very convenient function for checking whether you have correlation in the residuals term, right? Um, right. So for example, let me just generate some residuals like, let's say, I'll just use the R norm function, just produce 1,000 residuals. So, so these will have the correct expected shape, right? So it's centered on 0 and has some standard deviation. So this would be a typical residual term. But you can use the autocorrelation function, ACF, on the residuals from a fitted model, and you can check if the residuals are in fact independent of each other or not. And what this autocorrelation function ACF does is it looks at the correlation between every data point and itself. That will of course always be 1. Then it will look at the correlation between every data point and the next data point, and that should be 0, right? And the correlation between every data point and a data point with a lag of 2 behind after it. That means 2 data points downstream is the residual, correlated with the residual 2 steps downstream with a lag of 2, right? So if the residuals are completely uncorrelated, then the autocorrelation plot should show that the very first correlation of any data point with itself has to, of course, be 1, no question about that. But every subsequent lag, right, is going to be near 0. And the way you define near 0 is that there's a 95% confidence interval that they set up in the ACF plot. And if these correlations, these are all correlations here. If they fall within the interval, then um, that's an indication that they are not correlated. So this is just an accidental, you know, correlation that goes beyond the confidence interval. But really, we know that residual that I just generated is independent and identically distributed is because it's coming from the R norm function. So this is just an artifact of random variability, that you see some correlation here. So generally speaking, if you see something, if you see an ACF function on the residuals that looks like this, and this is all frequentist stuff. This is nothing to do with Bayes. Actually, this is just a standard frequentist approach to check for autocorrelations, in any vector of data, but in this case, residuals. So if you see a pattern like this where there's very little correlation, you will find that all these correlation lines here, they will fall within the confidence interval or almost within the confidence interval, like here, right? So this is a good way to check whether your model assumptions are being met or not in the residual stuff, right? I will discuss this again when I reach an example where we actually get a violation of this assumption, okay? All right, so where was I? Got a bit distracted here. So yeah, so I was just explaining these two equations here. So these are two ways to write down the linear model. And our goal, in this kind of simple modeling framework is that we have some intercept. We want to estimate the intercept. That's the whole point of the modeling here, right? We want to get an estimate of this intercept, but in the Bayesian framework, we will also get an estimate of the uncertainty on this intercept given the prior and the data, right? That's the big deal of the Bayesian approach, that you can actually start thinking directly about the uncertainty of the parameter that you're interested in studying, right? So, and of course, we are interested in the extent of the variability in the residuals, right? Because that tells us how noisy the data are. And so that helps us understand what the variability would be in the existing data and in future data that would be, could be generated if you were to run the study over and over again. So I've already mentioned this, that the normal likelihood is kind of questionable here, but right now it doesn't matter. Let's keep going. So the frequentist linear model would be fit like this. So the LM function in R fits a simple intercept only linear model. And this one is representing the intercept that I just mentioned here. It represents the intercept here, and that comes from the matrix formulation of the linear model, which I will talk about at some point. But right now, just now it's enough to know that the t is the dependent variable, tilde is like the equality sign, but what it really means is that the data are assumed to be generated from a distribution which has a particular mean, and that mean is represented by the intercept, which is written 1 here. And so once you fit this model, so underlyingly, of course, in this LM statement, the underlying assumption is exactly what I've written here, that the likelihood is Gaussian. And so all those assumptions are implicit in this LM function. Okay? And so once I fit the model, I've saved it as an object M, and then I can examine the coefficients. In the coefficients output, I only see the one coefficient that's there. That's the intercept estimate. And that intercept estimate is telling me the estimated mean button pressing time, button tapping time, right? And the sigma parameter estimate is 24 in these data, and that I can extract from the model as well. This is all frequentist stuff, right? And you can see that this is really 168.63 is really the estimate of the average button pressing time, because when I type mean on the button pressing time, I get exactly the same number, right? And the standard deviation is also easily computed from just looking at the vector t and running it through the ST function. So that's the meaning of these two parameters in the model. The intercept is telling me the mean button pressing time, and this is telling me the variability in the button pressing time, right? Okay, so the interesting problem that is novel now for us, as data analysts in the Bayesian framework, the interesting problem is that we now need to define some prior distributions on mu and sigma. And so you will often find, in textbooks and many introductions to Bayes, that people will come up with very flat priors for the parameters, or very what they call uninformative priors for the parameters. And an example of these would be what I'm showing here. For mu, you could have a uniform prior that goes from 0 to 60 seconds. Okay, so this is button pressing time. 60 seconds is an insanely long time. So for button pressing, so what this amounts to saying is that, where is it gone? Sorry. So what it amounts to saying is that my mu parameter, the prior on the mu parameter, so this is milliseconds, right, is assuming that all possible values between 0 and 60,000 milliseconds are equally likely. That's what a uniform prior. That's what a uniform prior implies on the mu parameter, right? Which is very, very unrealistic, but uh, as you will see, it's not exactly harmful. It's not gonna be very influential in determining what's gonna happen here. Okay, and so similarly for sigma, we could also define a uniform prior which allows 0 to 2000 milliseconds with equal likelihood, right? So we can now try to figure out what would happen if we were to fit a Bayesian model with these kinds of priors. And the way we are going to do that is that we are going to use a front end for Stan called BRMS. So there's a package called BRMS, and there's a function in that package called BRM, which does the same thing that the linear model function does in the frequentist framework. It has exactly the same syntax, but it has a little bit more detail in it because we need to specify priors as well. And also the BRM function explicitly allows you to decide on what the underlying likelihood function is. That's not available to you in the LM function. In the LM function, all you have is the Gaussian likelihood, right? So in the BRM function, you decide on the likelihood function. And here we are choosing the Gaussian just for convenience. And so here's my syntax, as just like the LM syntax. What's new here? One thing that's new here is the prior specification, right? So those are the two priors I just mentioned. Notice that I have to define a lower bound of 0 here, LB equal to 0, LB equal to 0 in the syntax here when I'm defining the priors for the intercept and for sigma, right? Here's the prior for the intercept, here's the prior for the sigma. And even though I write the prior to be a uniform bounded from below and above by 0 and 60,000, I still have to write the lower and upper bound separately inside this prior function, okay? Inside this prior function here. And the reason for that, if I remember correctly, is that I think the reason is that the Hamiltonian Monte Carlo sampler has to be told explicitly not to look beyond 0 and beyond 60,000 for the intercept when it's trying to do sampling. So it should never start with a random value beyond that range, and it should not go into that range for sampling at all. I think that's probably the reason, right? I've forgotten the exact reason. This is the BRMS specific specification, right? In Stan, we won't encounter this because this syntax. This is just for BRMS. So in any case, we have defined the priors now. And notice here, we have specified 4 chains, like I explained in the HMC lecture. We have set our iterations at 2000, and we've set up a warm up at 1000. So the warm up refers to the fact that in the beginning, the HMC sampler may not be sampling from the correct distribution. So we drop the first 1000 samples and we only take the second 1000 samples in each chain, so that we don't get any of the wild explorations of the HMC sampler. We want to wait until the sampler settled onto the distribution and is consistently sampling from the distribution before we start collecting the samples. So that's why we have a warm up of 1000 where we just throw away the samples. Don't reject them. I mean, we throw them away, and we only take the last 1000 samples from each chain. So there are 4 chains. Therefore, we have 4000 samples, right? That's what will happen in the end. Okay, so this I have already explained the components of the model, right? So let me just move on. This I've also explained iterations, chains, and warm-ups and all that. So the end product of this model can be now summarized graphically by plotting using the plot function. This plot function is actually this recognizes that we are working with a BRMS object. This fit underscore press is the model I just fit this model here, right? So this is the BRM object. And so the plot function will recognize that this is the BRM object and it extracts the correct, parameters and the relevant parameters and the chains so that you can see the fat hairy caterpillars in the output, right? So what this shows me is the posterior distribution of the intercept, posterior distribution of sigma, and the overlapping chains, which are mixing nicely over here. Okay, so this is a good visual check, which tells you that the chains have mixed nicely. Therefore, the sampler has converged. That's what we say, that the sampler converged onto the posterior distribution. So everything worked out well. You can also try this model using ShinyStan. So ShinyStan is an internet-based kind of graphical interface. Shall we try this? Which actually is pretty neat and gives you a lot more detail, which you can get into once you start looking at the stand documentation. Um, Let me just run the code here. Yeah, let me run all the code up to here and see how this goes, right? So I'm fitting the fit press model. And of course, one thing to notice is that even such a simple model takes quite a while to fit relative to the LM function. That will usually be true, right? So it's a little bit annoying that the Stan program takes so long, but what's going on here is that the BRM syntax is being translated into Stan syntax, and then the Stan syntax is being used to compile a C++ file, and then all that takes time. So it takes a little bit of time to do it. So here are the posteriors again. You can see them, right? This is what I just showed you in my slides. And so I'm going to launch ShinyStan and see what happens. Maybe I don't even have ShinyStan. Yeah, I don't have it. Sorry. Let me just install it. Right. So this should install ShinyStan, hopefully. Right. So now when I load ShinyStan, what should happen is when I type launch underscore ShinyStan for the FitPress model, it's going to give me a bunch of graphical, summaries that helps me understand the properties of the fitted model, right? So what I'm looking at here, this is not super easy to see here, but here's my intercept and sigma. Hey, what's going on here? Sorry, I'm confused. I don't know what this is, to be honest. So here I should be seeing the, oh yeah, right. No, I'm sorry. What's happening is my screen is so dirty. I can't even tell which ones are the dots here. Okay, so here's my intercept estimate, which should be something like 160 something, and this is the 24 something sigma estimate. And we are not going to talk about this right now, so this we can discuss later. But I think this it's showing the intercept twice for some reason, but this is a surprise to me because I don't never use this thing, so I don't really know why it's showing this strange duplication of the intercept posterior. But what it's showing is the mean of the intercept of the posterior, sorry, the mean of the posterior and the 95% credible interval. That's the error bar that you're seeing it. Not very easy to see. You might want to see the results in a LaTeX table, right? So you could actually extract this and stick it into your, LaTeX file. And um, does this work? Let me try this. So if you're writing a paper or something and you want to generate a summary of your results or something like that, you could certainly, you know, um, produce. Oh, this didn't work. Interesting. I didn't know that this would work, but let me show you how this would work. Okay. So, um, so when let's say I'm writing a paper or something. Um, um, here we go, right? So let's say I'm writing a paper and I want to put in the results of an analysis. I could just plug it in here and save this as, just call it untitled for now. Let's call it an example, I guess, right? So that's good enough, right? So what I want to do is I want to report the results of my analysis in a table. I could do that pretty easily. Why is this not working? Oh, this is embarrassing. Okay, so what happened was I don't have the right package of LaTeX installed here, but basically I could get a nice summary table that I can plug into my paper. But of course, you don't need to report every single detail of this output here. Okay, so really the important thing is the mean and these 95% credible intervals. So in practice, when I'm actually reporting results, I would generally not report any of these other things, which I will explain very soon. Okay, so the thing that we are really interested in is the posterior mean and the posterior 95% credible interval, right? So this lower bound, and I meant this lower bound and this upper bound, not the 50th quantile. So I would report this number, and this number for the posterior distribution of the intercept, and similarly for the sigma. Okay, so this shiny stand thing is pretty useful, I guess, if you want to look at summary statistics and the parameters plot and so on graphically. For these simple models, it's not super interesting, but for more complex models, it could be interesting because you might have some problems with chain convergence and so on. So you can check that. Here's the autocorrelation plot I just mentioned. You can see that the samples are not autocorrelated here, right? So that's what we are seeing here, that they are independent. So, and you can include the warm up too, right? So you can play around with this and see what happens with the samples when you include the warm up and not. Okay, that's for the intercept. You could do that for the, I guess there must be sigma as well here, right? For the sigma parameter here, right? So that's the sigma parameter that you get posterior arm. So that's Shiny Stand. You can play with it if you want to. And of course, one other important thing with Shiny Stand, which I didn't mention, is that there's some diagnostic plots that they also provide. So these are showing you the the trajectory of the Hamiltonian Monte Carlo algorithm in action. So this we will discuss in later chapters, probably in base 2 or in the second part of this course or in later chapters in the book, I mean, right? So, okay, sorry, that was a digression now. I just really got sidetracked by Shiny Stan. So, okay, so I've already explained that we can get graphical summaries of the posteriors from the model, but you can also extract the posteriors as vectors, okay? And so, for example, with as draws data frame, what you're doing here is that you're extracting the posterior distributions of each of the parameters. And what you get as a result of running this command is that you get a data frame that contains in one column the posterior samples for the intercept and the posterior samples for sigma. These guys we don't care about right now. I'll talk about all this later, okay? And so it's showing you giving you the posterior samples, which you can now do statistics on, right? So for example, you can calculate the mean, and you can calculate the mean from the posterior samples for the intercept and for the slope. You can calculate the 95% credible intervals. So instead of relying on, the shiny stan or the summary output to give you the statistics, you can actually derive them yourself by extracting the posteriors and then plot them however you want to plot them, right? Using whatever customized, graphical summaries you want to use. So that can be very convenient to have access to the posterior samples, okay? That will be very convenient. All right, so here's doing the same thing with sigma, computing the summary statistics, and so that's the basic machine, the workflow for fitting linear models in the Bayesian framework. We're going to define some likelihood function. We're going to define the structure of the model, the priors, and then we can just plot the posteriors and do summary statistics on the posteriors for now, right? Because right now we are focused on estimating figuring out the properties of the posterior. So two important things that are standardly part of the Bayesian approach to data analysis is doing prior predictive checks and posterior predictive checks. This is not something that we normally do in the frequentist framework. And indeed, you can't do prior predictive checks in the frequentist framework because there are no priors. But in the Bayesian framework, because we have prior specifications on the mu and sigma parameters in this example, we can just run the model with after drawing samples from the prior, we can just generate predictions from the data without having seen any, sorry, we can generate predictions from the model without looking at any of the data at all, right? So all we have is the model specification, which includes the prior specification, and we can use the prior specification and the likelihood to just produce simulated data, which counts as prior predictive data because we haven't seen the data yet at all, right? And then the other kind of check that we will do on the model is called a posterior predictive check, where after we have fitted the model and obtained the posterior distributions for the parameters, we use those posterior distributions and the likelihoods function that we defined to generate future data, right? That's posterior predictive data. So these two kinds of data distributions that we can generate are very important for model validation, right? They help us understand whether the model makes sense at all. The prior predictive simulated data that we'll produce will help us understand whether the priors that we specified make any sense at all, right? So if you have a nonsensical prior on your parameters, like the ones we have right now, right? So the uniform priors are pretty nonsensical that we have. So in that situation, what will happen is that your prior predictive distributions of the data will be completely unrealistic, right? What that tells you is that you did not specify an appropriate prior if the data being produced by the model don't make any sense. And I will just show you an example of that. And similarly, once you fit the model to the data, now you have posterior distributions on the parameters, and now you're in a position to get the model to generate future data, having seen the current data that you have. And that is also a good sanity check to see if your model produces realistic data at all, right? So we will see examples of that soon. So let's take this unreasonable set of priors that I had chosen earlier and see what happens when we try to generate prior predictive data from the model and see what kind of data it produces. Okay, so the prior predictive data is basically just integrating out all the parameters. Sorry, my cat is crying right now. Right, so the prior predictive distribution will be sets of simulated data that we will generate, right? And these simulated data will be just integrating over all the parameters. So that's what a prior predictive distribution will amount to here, okay? So the procedure for generating prior predictive distributions is pretty straightforward. We're going to take a sample, one sample from each of the priors. So here's the R unit function that is used for generating one sample from the priors for each of the parameters, plug those samples into the probability density or mass function. So in our case, it's the R norm function. We plug in those mu and sigma, generate n data points. N could be any number of data points, right? So in this case, I'm just producing 5 data points. And so what that does is, here I've produced a prior predictive data set with length 5. Okay, that's what I ended up doing. And even if you just look at these data, you'll see that this is completely insane data, right? If this was button pressing time, then the model is producing 60 seconds, 20, 60 seconds, 58 seconds, 58 seconds, 59 seconds, 57 seconds button pressing times. I mean, that is not a reasonable um, predicted data set, right? Because button pressing will be in the hundreds of milliseconds, not seconds. Okay. So each of these 5 data points, and now I could do this multiple times. Okay, I could just keep doing this over and over again, and each time I would get a new data set, a new simulated data set. So each of these data sets is an imaginary or simulated data set based on the model specification. That means the likelihood and the priors. Okay. So here's some example data sets that I generated. I generated 4 data sets based on the prior specification, and you can see that they're completely nuts, right? This data distribution of button pressing times is in the very short range here. These are too long, right? These are all too long. So obviously the priors are not really good for what we are trying to do here, for the model that we're trying to fit. Okay. So what can we do? So this is where this is the moment where everybody starts to get really uncomfortable about Bayesian modeling, because now you have to actually think about your model. And we don't really like to think about our models, right? So we like everything to be automated and let the data speak for themselves, so to speak, right? But in the Bayesian framework, because the priors can play an important part in deriving the posteriors, as I have explained in the analytical Bayes lectures earlier. We are going to have to think about what a reasonable set of priors would be for our problem. And so, although there's no standard terminology for different names for different types of priors, we just came up with a range of names that we use in our textbook so that we can refer to them. So the kind of priors that I showed you earlier, with the uniform priors, those we are calling flat uninformative priors, right? For obvious reasons, right? Then the next kind of prior that we could consider using, one class of priors that we could consider using are called regularizing priors. And these are priors that somehow constrain the parameters support such that you don't get an unconstrained range of values. So what I mean by that is that an example of a regularizing prior would be something like this. So that's the one that I'm showing you here. So I could have, I could say that, okay, I'm going to set up an unconstrained normal distribution centered on 0, but with a standard deviation of, what was that? What did I say? 1000, right? 1000. This is on the millisecond scale, okay? This is milliseconds. So, and then what I would do is I could say that, okay, I'm going to truncate this distribution and ignore this part of the distribution. So then the way we will write that in our textbook is that we'll say this is a truncated normal distribution with this mean and standard deviation. So obviously the mean will now shift, right? Because the distribution now is only this part of the distribution, right? Therefore, the mean will shift to the right somewhere, and the standard deviation will also change. So all those details we'll think about later, but this is one way of defining a regularizing prior. It's regularizing because it eliminates impossible values, right? So in a button pressing task, you can't have negative reading times. Therefore, we just constrain the prior to be only positive. So in a sense, it regularizes. And this fall in the density here is also has a regularizing function in that it downweights the extreme values. This is in contrast to the uniform prior, right? That I had defined earlier. So that's a useful thing to consider. Another one to consider is what we would call principal priors, which are not just regularizing, right? They are regularizing, but they also contain some principled decisions about what the mean and the standard deviation should be, based, for example, on domain knowledge or expertise or previous experiments that you might have done, right? So you can use prior knowledge or prior data even to decide on what a reasonable prior distribution might be. Need not be centered on zero, but it could be centered on a reasonable average button pressing time. So 250 milliseconds is a reasonable button pressing time, actually, if you look at the literature, right? So this is a principal prior because it's based on knowledge, prior knowledge, prior experience, prior belief, right? So all these kinds of prior information can be brought into the picture here in the prior. And this is one of the more powerful, you know, properties of the Bayesian approach, which is that you can always build on what you already know, right? That is not possible in the frequentist framework. In the frequentist framework, you always start from scratch, right? Because all you ever do is that you obtain maximum likelihood estimates of your parameters, and they are what they are, and you base your inferences on those, right? In the Bayesian framework, the priors can be brought into the picture and can be made to play an influential role if you have significant prior knowledge. And this can be very, very useful, as you will see later on when we look at more complicated problems. Okay, and then finally, the last class of priors that I'm mentioning here are the informative priors. So they don't look very different from principal priors, but one thing you'll notice is that they are much tighter. The informative prior here is much tighter, and it uh, carries a lot more information now. This informative prior is carrying a lot more information than this principal prior here. So I'm gonna have to take a little break here for the moment because my cat is crying for my attention. So what I'm gonna do is I'm just gonna pause my video and just play with my cat for a minute and just come back. Okay, so coming back to my slides. Right. So these are four basic classes of priors that we will consider whenever we are working on a modeling problem. And you will of course see many applications of this later. But let's think about why we would want to consider multiple types of priors in our data analysis. One reason why we might want to do that, or why we want to consider different priors, is to find out whether the priors are heavily influencing our posteriors or not. Right? So this is called a sensitivity analysis. When we fit the model with a range of different priors, so going from flat uninformative to informative priors, this is called a sensitivity analysis, and it's very, very useful for understanding how the priors influencing the posterior. What you will find is that in practice, if you have sufficient data, you will find that the prior will often have very little impact on the posterior unless you're using really informative priors. Right? Now, the importance of the priors in influencing the posterior will become very important later on when we start looking at hypothesis testing using Bayes factors. But when we are doing estimation, when we are just trying to figure out What I mean by estimation is when we are just trying to figure out the posterior distributions of the parameters, right? At this moment, when I'm looking at this posterior for the intercept and the posterior for the sigma, I'm just trying to get a descriptive summary of what the posterior is. Here I'm getting a graphical summary, but I could do a descriptive summary with those quantile, the 95% credible intervals, blah, 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 right? This gives me a descriptive summary of the posterior distribution. This is an estimation step. At this moment, I'm not doing any hypothesis testing, right? So by just eyeballing this posterior, I'm not trying to say that, okay, I have evidence that button pressing time is not, 150 milliseconds or something like that. That kind of hypothesis test requires extra work. And there, the prior specification can be very, very influential. So that's why it's important to become aware quite early of the importance of the prior in the model specification. So the way we would investigate the effect of the prior is by a sensitivity analysis. And so let's see how this works. Okay, so we'll refit the model with an even more uninformative prior than the one we had, right? So this time we have a completely insane prior, or not that the first one was not insane. The first prior was a uniform 0 to 60,000 milliseconds. This one is from minus 10 to the power of 6 to 10 to the power of 6 milliseconds, whatever that means, it's allowing impossible values for mu as well, right? So this prior is making the explicit statement that you could have negative button pressing times, okay? That's what I mean by an insane prior. And for the sigma, we've got an unusually large range of plausible values, which also doesn't make any sense as such, right? So So when we fit this model, okay, so let's say we fit the model with these priors. The the earlier model estimates that we had, they look like this, right? This was the fit press model with the uniform priors. And if you look at the 95% confidence interval or credible interval, sorry, you see that it ranges from 166 to 171. With our uninformative priors, right? Uninformative uniform priors, we've got a range that is pretty much the same as the first set of priors that I had used, right? So you can see that just is shifting to this insane set of priors doesn't actually change the posterior much. So that's an example of the prior not really influencing the posterior that much. And the reason for that is actually that we have enough data here and the maximum likelihood estimate is actually dominating in determining the posterior mean and so on. Like I explained earlier, if you have sufficient data, the the posterior will be closer to the likelihood estimate. All right, so we can go to the other extreme now. So this is our sensitivity analysis in action. And we can try to fit the model with an informative prior, right? With a mean 400 and standard deviation 10. That's a very tight prior, okay, on mu. And similarly, a very tight truncated prior on sigma, okay? Notice that for sigma, I will always have to define a truncated prior, truncated at 0, because sigma can never be less than 0, right? It has to be a positive value. So now let's compare all the three credible intervals for the intercept, right? So it was 166, 171 for the original model that I fit with the very uninformative priors. I got 165, 171, which is pretty similar. And for the informative priors, however, I see a shift to the right of the credible interval. You see that? And so you can see that the interval has become relatively tight compared to the other two cases, and it's shifted a little bit to the right. So you can see that these priors, this tight prior is actually pushing the posterior to the right a little bit. You can see that in the credible intervals moving to the right here. Okay. So there you can see that with a very informative prior, you end up with the posterior being influenced more by the prior specification. So here's the principal prior. So what's different from the informative prior is that the standard deviation is quite large. And so let's take a look at what happens here. So this was our informative prior, 170 to 175. With the principal prior, because we allowed more uncertainty again, right? We are back to 166, 171, 166, 171, right? So we don't see much difference. So the only difference that we see is that in the informative priors, we see a slight shift to the right, but nothing dramatic, right? And in all these priors, for all these models with different priors, we get roughly the same posterior distribution, right? There's not much impact of the prior on the posterior. So that's an example of a sensitivity analysis tells us, what the influence of the prior is going to be on the posterior. This can be useful to do if you're trying to establish whether your posterior is being affected by uh, your prior, and you're concerned that you might be bringing in too much information into your model through the prior, and you don't want to overly influence the the posterior via the prior. And there will be examples of this later on, so it'll become more concrete later on. In any case, the upshot of this sensitivity analysis is that we don't really see much effect of the prior on the posterior. So that's useful to know, right? And the reason for that, as I said, was that we have enough data. When we have sparse data, then the situation will be different. Then if you have very little data, then the informative prior is going to dominate in determining the posterior. So it'll be almost as if you didn't learn anything from the data at all. What you got back in the posterior is what you had in the prior in the first place. So you didn't learn anything new from the analysis in that case, right? All right. So So that's a good, I think, introduction into stepping beyond the linear modeling framework in the frequentist setting to the Bayesian setting, because we learned two important things. One was prior predictive checks to establish whether the prior makes any sense. And the other thing was a sensitivity analysis to check what the influence of the prior is on the posterior. So I'll give you some exercises. I won't ask you to do this right now, but I will give you some homework exercises on trying out some priors in some different settings to see what happens. Okay, so you'll get some experience in in sensitivity analyses and in generating prior predictive distributions. Okay. So one important use of the prior predictive distributions check is to use it to decide if your priors are reasonable. This is before you've seen any data, by the way. So you don't actually look at the data and then decide what your priors are going to be. That would not be a prior anymore, right? So you should be coming up with your priors before actually setting up your data, collecting your data. So what we typically do is that when we are planning an experiment, we will set up the entire statistical workflow with simulated data and lay out the entire analysis plan in advance and lay out the model and the priors and everything. Everything's fixed in advance. And then once that is done, then we start collecting data, and once the data come in, we just replace the simulated data with the actual data. And then we run the entire workflow without touching anything. So that way, there is no room for us to fiddle with the model, fiddle with the data to try to, manipulate the results to suit ourselves, right? Although, of course, we don't want to do that. There is a human tendency to fool yourself. It's very easy to fool yourself into thinking that you found something important And often that can happen when you know, delete some data or trim some data or remove some inconvenient data points and make your data look better than they actually do look, you know. So to prevent that kind of fiddling around with data and to save ourselves from ourselves, essentially, what we do is we lay out the workflow in advance. And then once the data come in, we just run it through the model, right? Without touching anything. Of course, you're of course free after you've done this kind of pre-planned analysis to do exploratory analysis. That's a separate step, of course. And exploration is great. You should do that, of course. But the planned analysis and the exploratory analysis should be kept distinct from each other. Otherwise, you run the danger of mistaking noise for signal, right? Because it's very easy to find important looking patterns in the data which are purely a consequence of noise, right? It's noise is a very amazing thing because it can look very systematic, right? Okay, so the next topic that I have to cover is posterior predictive distributions. I'm gonna stop this video now because I don't want it to be too long, and I will come back with a second part and finish this recording.